This is Chapter 10, which is all about bonding. So discussing Chapter 10, before we kind of get into, we're going to start with drawing Lewis structures. Before we do that, we kind of have to remind you what valence electrons are. From the last chapter, remember we learned that valence electrons for any main group element, that means not the transition groups, but groups 1, 2, and 13 through 18, is equal to the last digit of the group number, except for helium. Helium, even though it's in group 18, only has 2 valence electrons. That first period is a little bit bizarre because the complete orbital would only hold 2 electrons, whereas all the others can hold 8 electrons. Okay, so it's equal to the last digit of the group number. So for instance, aluminum is in group 13, 3 valence electrons. Hydrogen in group 1, 1 valence electron. So we're going to use, every valence electron is going to be represented by a dot in a Lewis structure. The dots are placed around the element, 2 per side, so you have a top and a bottom. So we're going to use an element symbol, and you're going to have the top and the bottom and the left and the right. So each side can hold 2 dots, 4 sides, 8 electrons. So although the exact location of dots is not critical, what is critical is that we first have to put dots in singly and only pair up if there's no free side available. There will be an exception with helium, described later. So let's see what this really looks like. So for instance, for oxygen, I could have gotten the valence electrons from its electron configuration. 1s2, 2s2, 2p4. Valence is defined as the number of electrons in the outermost occupied orbital, so that's the level 2. So I have 2 and 4 for a total of 6. Or I could have said that oxygen is in group 16. The last digit of 16 is 6 valence electrons. Okay, so this would be what its Lewis dot structure looks like. I start with a chemical symbol O, and I start putting around the 6 dots, almost like I'm dealing out cards. 1, 2, 3, 4, 5, 6. And I end up with this structure. What we mean when we say that the exact location isn't critical, if I had put 2 dots on this side and 1 dot on the top, it's still the same thing. In other words, when I'm done, oxygen should have a total of 6 dots, and 2 sides should have 2 dots on them, and the other 2 sides should have just 1 dot on them. But which side has 2 and which side has 1 is not relevant. If we go through all of the period 2 elements, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, this is what their Lewis dot structures look like. This is kind of important because neon is in group 18. All of the elements in group 18 are going to have 8 electrons, so they're all going to look like this. Similarly, carbon is in group 14. All of the elements in that group are going to have a similar structure. What will change is the chemical symbol in the middle. So we begin to see 1 electron, 2 electrons. Note that 2 sides have 1 dot in it, and the other 2 sides have no dots in it. 3 electrons, 4 electrons, 5, 6, 7, 8. So this is what our Lewis dot structures look like. And as we remember, hopefully we learned a little bit before, but if not, we're looking, all the atoms are trying to get to, they are particularly stable when they have 8 valence electrons. We've observed this behavior and noticed that they form ions such that they have 8 valence electrons. And it's very easy to see when it has 8 valence electrons because it means 2 dots on all 4 sides. So it's quickly easy to see in a bonded arrangement, is that shell fully occupied or not? There are some exceptions. Remember, hydrogen and helium are in group 1, in period 1, and that first energy level can only hold 2 electrons. So they're trying to get an octet. Oct, remember, is the prefix for 8. Almost all elements are trying to get 8. Hydrogen and helium are exceptions. They're going to be stable with 2. Also, lithium and beryllium tend to lose electrons, and they'll be trying to get to 2. Okay, so the octet rule, in summary, is saying that in the bonding, atoms are going to transfer or share electrons so that at the end of the bonding, they've accomplished having a complete outer shell of valence electrons with 8 valence electrons, and that's why we call it the octet rule. And again, it applies to all main group elements, transition metals. They do weird stuff. We're not going to talk about them. Hydrogen, helium, lithium, and beryllium, hydrogen, lithium, and beryllium particularly, are going to aim for 2. Helium already has 2, that's why it's not listed. So those are the 2 exceptions, they really have the duet rule. But we still refer to the concept of octet rule as bonding in order to achieve a full set of valence electrons. Okay, let's look at a particular ionic compound. Now, we've already really gone through and done ionic compounds a little bit in chapter 5, but now we're really looking at the nature of the bonding. So if I look at potassium's in group 1, so it has 1 valence electron, 1 dot. Chlorine is in group 17, it has 7 valence electrons, 1, 2, 3, 4, 5, 6, 7. I would get this valence structure. And I can see chlorine needs 1 more. Potassium, if it loses 1, there would no longer be any electrons in the 4th energy level, and the 3rd energy level would be completely full. So it would have a full octet, even though it has no dots showing. It would be full because now valence is defined as the level 3 instead of level 4. So we know that metals are going to lose electrons in ionic bonding, and they're going to lose electrons such that they end up with none. So potassium is going to can give up 1 electron. Chlorine needs 1 more electron to be full, so 1 potassium, 1 chlorine will work. So as we see, the potassium transfers up. Let's see if I can't move this. Potassium has no electrons. Note that when it lost that electron, it now has a positive charge. I have to show that charge. Chlorine has an extra electron. Because of that, it has a negative charge. Generally, we draw brackets around these if they have an extra charge, especially for negative ones, to sort of say somewhere, but in the homework I think they can't do brackets, so you do need to indicate the charge. The brackets are sort of optional. Another example would be magnesium and oxygen. Magnesium group 2, so it has 2 valence electrons. Oxygen group 16, it has 6 valence electrons, so I can see that oxygen is missing 2 electrons. The left and the bottom side need another electron. Magnesium happens to have 2 electrons, and it's a metal. Metals lose electrons, non-metals are going to gain. So the magnesium gives up its 2 electrons, 1 to here, 1 to here. And this is now gained 2 electrons, it has a negative 2 charge. Magnesium has lost 2 electrons, it has a positive 2 charge. So this is a way that I can do ionic bonding. So we're going to do, these are Lewis structures of showing ionic bonding. And as we're saying, one way that we used previously in chapter 5 to figure out what the chemical formula of an ionic compound was to determine what ion charge it can make and then use that ion charge to balance it out. Essentially, this is another way to visually do it. We're going to see how many electrons each metal has to give up and how many electrons each non-metal needs, and I can transfer. So if I have a sodium and a sulfur, sodium's group 1, it has 1 electron. Sulfur's group 16, it has 6 electrons. It needs 2 more. The sodium can only provide 1, so what that means is I'll need 2 sodiums. This sodium provides 1, has a positive charge. This sodium provides another 1 and has a positive charge. This sulfur ended up gaining 2 electrons, it has a negative 2 charge. So this could help me recognize that the chemical formula for sodium and sulfur is Na2S. This would be the sodium sulfide chemical formula. Now, you've used algebra and ion charges from chapter 5 to accomplish this. This is another way to accomplish it. But where things start to get powerful is when I start to do covalent Lewis structures. When we talked about covalent compounds in chapter 5, we discussed that they don't have a predictable chemical formula. We can't determine what the ratio of one element to another element would be. Those 2 nonmetals, we would have to be given the subscripts. Therefore, in those names, remember we had di and tri and tetra, and we had to tell you how many of each. However, we can start understanding what's going on with the bonding and make some better predictions when we can draw covalent structures. So this is a covalent Lewis structure. It's a little different. In covalent structures, remember, there are no ions. A covalent compound is formed from sharing of electrons. So it's going to look a little different. In theory, we're going to represent the covalent bonding by allowing neighboring atoms to share a pair of valence electrons in order to each get full octets or duet for hydrogen. So if we look at water, hydrogen has 1 electron, It needs 2, so it needs 1 more. Oxygen has 6 electrons, it needs 2 more. Remember, these are now both nonmetals, so nonmetals gain electrons. They both need to gain. This needs 1 more, this needs 2 more. I can accomplish this with 2 hydrogens. So notice on this side, this hydrogen supplied its electron. Oxygen had an electron there, and that's that pair. In this drawing, I would imagine that this side would have a single dot, and this side has double dots. And the same thing's happening over here. Note at the end of the day, we can kind of envision when we're counting our octets or duets, we really want to sort of circle, and I'm going to double count this pair. This is how we do some funny accounting. Hydrogen, if I look at what is in its outer shell, we're going to consider this overlap area between 2 neighboring atoms to belong to both. So this hydrogen has 2 dots, it needs a duet, it's fulfilled. This hydrogen has 2 dots, it needs 2, it's fulfilled. This oxygen needs 8, 1, 2, 3, 4, 5, 6, 7, 8, it has its octet filled. So note that this pair and this pair got counted twice. This is what we were referring to as a covalent bond. It's a pair of shared electrons that was provided from from 2 neighboring atoms to share that set of electrons. And they get to both count it. This explains our 7 diatomics. Our 7 diatomics are all nonmetals. Remember, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and they all accomplish those diatomic bonding by forming covalent bonds. So if we look at chlorine, chlorine is group 17, it has 7 electrons. And we look at another one, note that they each need 1. If I swap sides and put that side on the one that's in between them, and this one that's in between them, we can see that this is the shared pair of electrons. Oftentimes, so this is an acceptable way to show a covalent bond, but another acceptable way is to show a bond this way, is to draw a line to replace that pair. So that line represents 2 pair of shared electrons. And this is true for the other diatomics as well. Let's go through how to draw a Lewis structure. There's a lot of hints. Okay, first, I want to begin by putting the lowest valence electron element in the middle. So I have to look at them and consider the valency of each of the elements in the compound. I'm given a chemical formula, for instance, I think SCl2 might be an example. I think that's the one I'm going to use in a minute. I don't want to consider hydrogen as being a low valence element. I want to consider hydrogen as being a high valence element. Another way of thinking of hydrogen is that although it only has 1, it only needs 1 more to fulfill its duet. So it's missing just 1, whereas something with a valence of 5 needs 3 more. So we're looking at the lowest valency, or in other words, which ones need the most amount of electrons. So lowest valence that's not hydrogen gets put in the center. All the other atoms listed in the chemical formula get placed symmetrically around it. For instance, sulfur, SCl2, S has a valency of 6, chlorine has a valency of 7, so we'll put S in the middle, and we'll put the 2 chlorines around it. In other words, I want sulfur to be the central atom. Okay, now I'm going to finish drawing Lewis dot structures for each of them. So I draw the 6 around sulfur, the 7 around chlorine, and the other 7 around chlorine. At this point, I need to kind of move them around. Now it matters which side has 2 dots and which side has 1 dot. I want the unpaired dots to be on a side that is facing another atom. So notice that chlorine, the bottom chlorine, its dot is on the top, and the sulfur has a 1 dot on the bottom. So those 2 are lined up to share. Same thing with the sulfur and the chlorine. Now as a student, when you're drawing these, inevitably they won't be on the right sides, so you may have to erase, and you can swap sides. If you have drawn it, if you had drawn sulfur and the unpaired electron was on the left and the double pairs of electrons on the bottom, you can sort of erase and move them and swap sides. So we swap sides so that this is the arrangement. And if you don't do that, this gets much harder. So it's really important to take the time to maneuver the dots so that the unpaired dots are facing another atom. Okay, and I put red and blue. We don't typically do that. I did it for visual clarity so we can see the red belonged to sulfur and the blue belonged to chlorine. going to circle pairs of unpaired electrons, or combine them, draw a line between them, something to indicate these two can bond, these two can bond. That's going to be by bonds. When I'm done, I'm going to redraw the covalent structure, replacing those circled dots with a line. So this becomes my structure. And notice that sometimes sometimes we can't do this for a molecule, it doesn't work, but we know that molecule exists. And so in some cases, we'll move electrons around from one atom to another. We're not going to get too much into that in this course, so we don't need to worry about that.